As you look at 5.7 deals with applications of exponential growth. And we mentioned in class that if something experiences exponential growth compounded at a regular interval, then we use the formula A equals P times 1 plus R divided by N to the NT power. But if something is continuously going through exponential growth, for example, if we had a colony of bacteria, had different pieces of bacteria throughout that colony, then their growth is something that is continuously happening in a controlled environment. If there's plenty of food available, if there's the right conditions, the right temperature, then these organisms are going to be going through mitosis. And as soon as they split into two different cells, then they're going to split again. And that's going to be continuously happening. It's not going to be like they grow and they wait a week and they grow again and they wait a week and they double again. They're constantly going to be going through this reproduction cycle. So if we look at our compounded interest formula, our growth formula, if we let the number of times that N occurs, the number of times that growth occurs per cycle, if we let it become more and more and more and more often, then we're letting N get bigger and bigger and bigger. So N is effectively going to infinity. So this formula turns into A equals P times E to the RT. If we look at just 1 plus 1 over N to the N power, if we let N get larger and larger and larger, it turns out that that is approaching the number that we refer to as E, which E is 2.7, and then several decimals, goes on forever actually, kind of like pi is a specific number that never terminates, never repeats. So if we're talking about continuous reproduction or continuous decay, exponential growth, then we're going to be using this particular formula. So let's work through an example. So the country has a growth rate of 3.4% per year. And the country currently has 5,979,000 people. And the country has 34 billion square yards. The area of the country is 34 billion square yards. So the question is, how long will it take this country, the population, until there is one person for every square yard? One person for every square yard. So first of all, let's write our exponential growth formula. So A equals P, which is 5,979,000, E to the R. R as a decimal is 0.034 times T. So that's the exponential growth function. A is a function of T. So if there are 34 billion yards and there's one person per square yard, that means that there would be 34 billion people. So we want to find out what would T need to be so that our amount of people is 34 billion. So that gives us an exponential equation. And like the exponential equations we solved in section 5.6, notice our variables in the exponent. Now, in reality, this would not be a continuous growth rate. The rate would change because as you get more and more people, it becomes more and more crowded, and that creates a whole variety of problems. But if it were possible to reach this population with a continuous constant growth rate, then this equation would give us how long that would take to happen. So when we're solving an exponential equation like this, we want the base and the exponent by itself. We don't want a coefficient out front. So we're going to divide both sides by the coefficient. So on the right side, those cancel. On the left side, 34 billion divided by 5,979,000 is about 568, let's call that 5687. So when solving exponential equations, we take log of both sides so that we can use the property of logs to pull our variable out of the exponent. But we also saw that if our base is e, it's most efficient to take the natural log of both sides instead of just regular log. Because if we can take the natural log of both sides, natural log is base e. If this base is e, natural log and e undo each other because they are inverses. So they undo each other, leaving an exponent. And then if we want to get t by itself, we divide both sides by 0.034. So those cancel. So t is natural log of 5687 divided by 0.034. So about 254 years. So in 2.5 centuries, there would be one person per square yard if that remained a constant rate. So let's look at another one. Let's suppose that a certain population had a growth rate of 7.1%, and we wanted to find the doubling time for that particular population. So we're looking for t. Now notice it doesn't tell us what the initial amount is. So if we fill in what we know, we don't know the final amount, we don't know the initial amount, we just know that the rate is 0.071, and we're looking for t. So t is what we're trying to find. But notice it says doubling time. So doubling time is how long does it take for our population to double. So if our population started out at 10, when it doubled, there would be 20. Or if it started out at 70, when it doubled, it would be 140. So regardless of what number we put in for the population, let's notice what's going to happen. If we divide to get rid of our coefficient, if our population starts out at 10 and it doubles to 20, 20 divided by 10 would be 2. If our population started out at 70 and it doubled to 140, when we get rid of our coefficient, we would still end up with 2. So we could say that our initial population is p. The amount when our population is doubled would be twice p. So we could do that. So if our initial population is p, when our population has doubled, we have twice p. So if we divide both sides to get rid of that coefficient, then yes, regardless of the initial population, if it's doubling when we get rid of our coefficient in front of the e, we have a 2 on the other side. Now to get rid of the e to make our exponent, or make t not be in the exponent anymore, we can take natural log of both sides. So natural log base e to a power, those are inverses, so those cancel, leaving us just the exponent. And then to get t by itself, we divide both sides. So t is whatever we get when we take natural log and divide by 0.071. So about 9.8 years. So if our growth rate is 7.1%, the amount of time it would take for us to double would be 9.8 years. So regardless if it's an exponential growth equation, this is the formula we're using, or it could say that something is continuously compounded. We substitute in the pieces we know, and then we solve for the unknowns.